Hi everyone, my name is Kuvina and welcome to Relativity Part 8. The Lorentz transform is arguably the most fundamental concept in all of special relativity. It's used on position over time graphs to switch between reference frames, and it can single-handedly account for all the relativistic effects that I've covered so far. In this episode, we will derive a formal definition of the transformation, then examine its properties, and see how it recontextualizes all of special relativity. But first, we need to get our bearings straight. We'll achieve this by starting with non-relativistic examples. So consider the following scenario. The triangles amber, blue, and cerise are racing from point A to point B, located at positions 2 and 7 meters respectively. Amber triangle uses the technique of no movement. They sit still at point A the whole time and don't perform very well. Blue triangle uses the technique of constant movement, hovering just above the ground and moving to the right at a constant velocity of 0.5 meters per second. Time equals distance over velocity, so it'll take 10 seconds for blue to go from A to B. Cerise triangle uses the technique of varying movement. They use a fan to get up to speed, which does take a while, but they eventually pass blue and actually end up winning the race. There's a lot going on in this example, so it helps to make a position over time graph. We'll represent these variables with x and t respectively. Amber maintains a constant position at point A, so their line is flat. Blue is at position 2 at time 0 and position 7 at time 10. Due to having a constant velocity, they have a straight line between these 2 points. Finally, cerise is also at position 2 at time 0, but actually at position 8.25 at time 10, and with the changing velocity, their line starts flat, then slopes up before flattening again. This is all pretty normal so far, so how does relativity factor in? Well, relativity is all about perspective. A reference frame is defined as a way to orient your coordinates in space and time, and is essentially just a perspective. The reference frame for a given observer is just the one that has them at position 0 the whole time. The reference frame in which the example was given actually belongs to this arbitrary point on the ground, since that's where position 0 is. But each of the observers, amber, blue, and cerise, will have their own reference frame. So let's take a look at those, starting with amber. Now, we could determine what it would look like by redoing the calculations, but there's no need. Instead, we could just transform the reference frame we already have. In the case of amber, this is extremely easy. Since their position in the original reference frame is a constant 2, in order to take them to 0, we just have to shift everything down by 2 meters. I'm going to call this a simple space shift, and simple time shifts are also possible. But of course, most of the time things aren't this simple. In the case of blue, their position is constantly changing, so a constant shift won't cut it. But what we can do is basically cut the graph into vertical slices and shift each slice such that it puts blue at 0. As you can see, in blue's reference frame, cerise changes which direction they're going, and amber moves constantly to the left, along with points A and B themselves. It might seem a bit weird to have the entire Earth moving, but it's still a valid perspective since there are no laws of physics being broken. Lastly, we'll look at cerise. The slice shifting does indeed still work. It actually brings cerise to a constant velocity and gives everyone else varying velocities. Again, pretty weird, but it does reflect what cerise actually sees. So shifting slices is pretty cool, but how could we define it mathematically? Well, defining transformations of a 2D surface is actually pretty simple as long as it's a linear transformation. For a transformation to be linear, there are 2 requirements. The origin never moves, and straight lines remain straight. These seem pretty restrictive, but they're actually more versatile than you'd think. With the origin requirement, for example, as long as the 2 observers meet up at some point, which is guaranteed for non-parallel straight lines, you can use a simple time shift to make that fixed point the origin. And when the lines are parallel, a simple space shift is all the transformation is anyway. But what about the straight line requirement? Well, in the context of these graphs, straight lines correspond to constant velocity, and there's a really useful fact related to that called the principle of relativity. It says that in an inertial reference frame, meaning a non-accelerating one, the laws of physics always remain consistent. Among these are Newton's laws of motion. The first of these, the law of inertia, says an object will maintain its constant velocity until acted on by an outside force. So if you're in an inertial reference frame, straight lines represent objects with 0 net forces, and if the reference frame you switch to is also inertial, these 0 force objects will still be represented by straight lines, satisfying the second requirement. In the example, cerise accelerates and therefore is not an inertial reference frame, but blue and amber both are. This means we can convert between them with a linear transformation, and in classical physics, this is known as the Galilean transform. By the way, the reason we know Cerise is the accelerating one is because they're the one experiencing a net force slowing them down, which is correctly shown in blue and amber's reference frames, but in Cerise's own reference frame, everyone else is accelerating despite no force. Alright, so now we know why we could use linear transformations, but why is that useful in the first place? Well, it's because linear transformations can be represented with matrix vector multiplication. If you're unfamiliar with how that works, I'll give a brief explanation. So points on the 2D plane will have an x and y component. In matrix land, we arrange these vertically, and this is known as a 2x1 vector. Depending on the context, it's also helpful to represent them as arrows from the origin pointing to that location. The transformation itself is represented by a 2x2 square of numbers known as a matrix. To execute the transformation, you take the point as an input vector, then multiply the matrix by it to get an output vector, and this tells you where the point ends up after the transformation. But how does that process actually go? Well, matrix multiplication has a relatively simple formula and intuition. I like to think of it as the vector turning and getting distributed across each row. Then you add the products within each row to get the output vector. Just as an example, consider the matrix 1, -2, 2, 3. Multiplying by the vector 2, -1 results in 4, 1, so the transformation moves this point from here to here. When applying a transformation to the entire 2D plane, we can visualize it by simply moving the grid lines, although keeping the old ones can be helpful to judge the new locations. When using matrices to transform spacetime, we usually use the horizontal axis for position and vertical axis for time. So in that case, our example would actually look like this, and the slices are horizontal. Also, we use x and t for the input vector, and x prime and t prime for the output. With those conventions established, it's now time for the derivation of the matrix representation of the Galilean transformation. Remember, the Galilean transform only applies to inertial reference frames, so both observers, which I'll call uppercase A and B, will be straight lines. If we assume the relative velocity is non-zero, they're guaranteed to intersect at some point. And if we assume you've done the necessary simple shifts beforehand, we could place that intersection at the origin. Now we just have to figure out the 4 numbers in the matrix, which I'm going to call A, B, C, and D. To do this, we'll form equations with specific vectors such that we know where they'll end up before and after. First of all, we'll get rid of observer A, since their line will only get in the way. Now, we know the transformation will bring observer B's line to the vertical axis, since that's what it means to switch to their reference frame. But how will this affect specific vectors? Something like the vector 1, 0 represents the point 1 meter to the right at time 0. The horizontal slice on which it's located already has observer B at position 0, so this is actually the one slice that doesn't move. Therefore, the vector won't move either. This means our matrix ABCD times 1, 0 equals 1, 0. Multiplying things out tells us A equals 1 and C equals 0, so we're already halfway done. Other than this one slice though, everything else depends on the relative velocity. If observer B is moving at v, then after 1 second there'll be v meters to the right, which corresponds to the vector v1. After the transformation, this slice will shift to the left to bring observer B to the center, but the height won't change, putting it at 0, 1. So this time, our equation is the matrix times v1 equals 0, 1. Multiplying things out tells us d equals 1 and v plus b equals 0, which means b equals negative v. With that, we finally have the full Galilean transform in matrix form, and if separate equations are more your thing, it's x prime equals x minus vt and t prime equals t. No matter what the velocity of observer B is, this matrix will shift the slices in such a way that brings them to the vertical axis, which represents their reference frame. But that was just the appetizer. Now it's time to upgrade to the Lorentz transform. It is a lot more complicated, but it can be derived the exact same way, which is why I introduced that process with the simpler Galilean transform. The Lorentz transform is essentially just the Galilean transform if it accounted for relativistic effects. These effects are shown in my list of rules, and each one has a spotlight episode in the series, so make sure to watch those if you want to learn more. To put things very simply, observers moving at near light speed will have time slow down and length get shorter. But the first 2 rules are the postulates of relativity, which everything is based on, and are technically all you need for the derivation, so let's take a look at those. The first postulate is just the principle of relativity from earlier, which is why we know we can still use a linear transformation. But the second postulate is known as invariance of c. It says that the speed of light c is the same in any inertial reference frame, and due to this, we know the Galilean transform can't still hold in relativity. When changing reference frames, the observer's speed goes from v to 0. But since the entire graph moves horizontally, any particle moving at c will have its velocity reduced. Of course, the speed of light is extremely fast, so even with v equals 15 million meters per second, that's still only 5% of c, so the shift barely affects it proportionally. This is why the transformations are approximately identical for small velocities, but when dealing with relativistic speeds, using the right one is very important. It's almost time for the derivation, but first we have to talk about units. The speed of light comes up all the time in equations, so using units where c equals 1 makes calculations way simpler. The official Lorentz transform works with any units, and I'll show how that works at the end, but for the derivation itself, I'm going to use years and light years. With that, let's begin. Since c is used for the speed of light, the transformation matrix will now be ABKD. Now, just like before, we know observer B's line will move to the center, but the method by which this occurs must be more complicated than the slices in order to preserve invariance of c. Since c equals 1, anything traveling at c will be represented by a line with a slope of 1. The one that passes through the origin has the equation x equals t, so any point on it has both of these coordinates equal. One of these is the vector 1, 1. Even though we don't know where it ends up, it must remain on this line to preserve invariance of c. Therefore, its corresponding output vector should have x prime and t prime equal, and therefore be of the form ss. This isn't a specific vector, so it gives less information, but it's a start. Multiplying things out, we find a plus b equals s and k plus d equals s, which combine to tell us a plus b equals k plus d, which we'll save for later. We can also use invariance of c in the other direction. Moving at c to the left, the vector -1, 1 must get mapped somewhere of the form -s, s. Multiplying it out, we get -s equals -a plus b, and s equals -k plus d. The first can become s equals a minus b, and combining them results in a minus b equals -k plus d. Now at this point, we'll combine it with the previous equation by adding them. B and k both cancel out, and we find that a equals d. And then substituting this in the first tells us that additionally, b equals k. This means the original matrix can actually be written as ABBA, so now we only have two things left to calculate. To do so, we'll use the same technique from earlier. At time 1 year, observer B will be at position v corresponding to the vector v1. Observer B sees themselves as stationary, so this vector should get mapped to the vertical axis, meaning the horizontal component x prime equals 0. But what about the vertical component? Using the slices of the Galilean transform would keep the height the same, making t prime 1. But this would assume time stays consistent across reference frames, which we can't assume. For now, all we know is that it's some value which we'll call g. After multiplying things out, we can see 0 equals AV plus B, and G equals BV plus A. The first of these becomes B equals -AV. We can then substitute this into both the original matrix and the other equation, at which point we can even factor out A to get G equals A times 1 minus V squared. Now if only we knew the value of G, we could easily solve for A to finish the matrix. Actually, we pretty much do know the value of G. In the original reference frame, observer B is moving, so they undergo time dilation. This means at time t equals 1, they will have aged less than 1 year. How much less depends on velocity. According to the formula, the amount they aged is square root of 1 minus v squared over c squared, and in our units, the c squared disappears. But in observer B's own reference frame, their age will perfectly match with time passed, so this is actually our value for g. Now we just have to solve for a. The 1 minus v squared by it is actually just square root of 1 minus v squared squared. So after dividing by it, we get some cancellation and end up with a equals 1 over square root of 1 minus v squared. This value has a special name. It's called the Lorentz factor and is represented with the Greek letter gamma. Technically, there's also a c squared in there, but in our units that just equals 1. Anyway, since a is just gamma, we've now completed the Lorentz transform matrix. We could also factor out gamma as a scalar in front of the matrix. And here's what it looks like in separate equation form. However, this technically isn't the full Lorentz transform for two reasons. First of all, it only has one spatial dimension, when in real life we have three, x, y, and z. If you define your coordinates such that the relative velocity is confined to the x dimension, the y and z dimensions remain unaffected. That's why I usually don't include them, but technically speaking, the full Lorentz transform is a 4x4 matrix that looks like this. The other technicality involves units. As mentioned earlier, this formulation uses units where c is 1. In reality, there are some hidden c's in here that aren't shown, but if we want the equation to work with any units, we need to find where they are. There are several ways to do this, but the simplest is to realize even with meters and seconds, x over c functions as a stand-in for position in light seconds, and v over c represents velocity as a fraction of c. Using these instead of v and x directly, the equation should still behave the same way. After substituting them in and simplifying, we've found our c's. Putting it back in matrix form looks like this. And since terms over c squared are basically zero at low velocities, this also shows why the Galilean transform approximates everyday life. With that, we'll add the Lorentz transform to the list of rules as number 7. But for the rest of the video, we'll be using natural units, so c equals 1. Now that we've derived the Lorentz transform, what does it actually look like? Well, it depends on velocity. If observer B has a low velocity relative to observer A, the shift will be small, but with a high velocity, we get a pretty major shift. What I'm going to do is have a slider that shows the velocity in the base reference frame of the observer whose reference frame we're currently looking at. This can be moved continuously to better intuit the transform. With relative velocity 0.7, the transform looks like this. But to see what's happening, we'll move the grid lines with it. As you can see, both vertical and horizontal lines get skewed, but in such a way that B is brought to where A was. If we instead switch to diagonal lines with slope plus or minus 1, you could see they do move around, but never change slope. In fact, the two that intersect the origin don't even move around. Due to this, the Lorentz transform can be thought of as shrinking on one diagonal and stretching along the other. Another way to visualize it is by graphing a bunch of random points and seeing how they react. If you look at the paths they trace out, you get this shape, which is half of a hyperbola. A hyperbola is in a sense the opposite of a circle, since bringing points to the center lowers them instead of raising them. Now let's take a look at how it's actually used in relativity. In this context, the graph is known as a Minkowski diagram, and the lines representing objects are called world lines. Each point on the diagram represents an event, basically just a time and place at which something can occur. If you connect two events with a straight line, the slope of the line tells you a lot about the relation between the events. If the slope is greater than 1, or less than -1, basically more vertical than horizontal, the relation is known as time-like. No matter the velocity of the transform, the relation will always remain time-like, and they'll happen in the same order. This is consistent with causality, since the second event could be caused by the first. If the slope is less than 1 and more than -1, the relation is space-like. They'll always remain space-like, meaning they won't switch positions, but they can happen in a different order depending on the reference frame. This doesn't violate causality because it's impossible for one event to cause or influence the other. To see why that's the case, we'll look at the third possibility. If the slope is exactly 1 or -1, the relation is called light-like, and this never changes due to invariance of c. The world line of a photon will be of this form, since they travel at c. And because information can never travel faster than c, this actually represents the maximum extent of causality stemming from a single event. Specifically, the area bounded by light-like lines in both directions is called a light cone, and an event can only affect other events within its light cone. Space-like events are never in each other's light cones, but time-like events always are, explaining causality. Now it's time for the exciting part. We're going to go through various examples throughout the series and see how the Lorentz transform recontextualizes them. We'll start with the long-awaited return of Mary and Botan. They both start off on Earth at the age of 20. Botan stays on Earth for at least the next 5 years, while Mary takes off in her ship, traveling at 0.6 c. On the graph, the scenario looks like this. Their world lines have the same starting point, 0, 0. But Botan's endpoint is 0, 5, while Mary's is 3, 5. So what events do these points represent? The origin is the departure, where they're both 20. Since this is Botan's reference frame, her own endpoint, being at time 5, represents the event of her turning 25. But since Mary moves at 0.6 c, she experiences time dilation and will be less than 25 at the time. Using the formula, we find she ages 4 years, so the event is her turning 24. We can demonstrate the time dilation with evenly spaced points representing integer ages, in which case Botan has 5 segments, but Mary only has 4. If we use the Lorentz transform to switch to Mary's perspective, her endpoint gets mapped to t equals 4, which makes sense because an observer always experiences time normally in their own reference frame, so it takes 4 years for Mary to turn 24. However, despite being previously simultaneous, Botan's endpoint now gets mapped further out. This represents the reciprocity of time dilation. In Mary's reference frame, Botan doesn't turn 25 until year 6.25, and when Mary turns 24, Botan is only 23.2. If we draw a flat line connecting these events, then it represents simultaneity in Mary's reference frame. We can actually make simultaneity lines for each year. If we switch back to Botan's reference frame, they shift a bit. This is a representation of relativity of simultaneity. In this reference frame, Mary perceives things to the left as they are a bit earlier than things to the right, which explains why Mary at age 24 has Botan at age 23.2, not 25. In general, if an observer's world line has a slope of k, their simultaneity lines will have a slope of 1 over k. This provides another intuition for the reciprocity of time dilation. In the reference frame that has them going opposite directions, their simultaneity lines will both portray each other as younger. Now, relativity of simultaneity tells us the only way to guarantee two events are simultaneous in all reference frames is if they also happen in the same place. In the past, we synced up events using photon signals, and if you're curious, here's what that example looks like. But with the Lorentz transform, it's now easier to describe events that aren't synced up. In this example, events A, B, and C are simultaneous, but after switching, they occur in the order C, B, A, which can be seen by executing the transform or just using simultaneity lines. And this same principle even applies with more complicated distributions. Next up, let's look at length contraction. In the example with Mary and Botan, we can give Mary a destination, a star that's 3 light years away. Its world line will be vertical, just like that of Botan on Earth, but 3 units to the right. If we switch to Mary's reference frame, both world lines become slanted, and at any given moment, the distance between them is now only 2.4 light years, just like the predictions. But this is just the distance between objects. What about objects getting contracted themselves? Well, if you place down a ladder with a proper length of 4 units, and then transform by 0.6 c, you'll notice it gets longer and is now 5 units long. But hold up a minute. According to length contraction, it should get shorter, not longer, so why do we get the opposite result? Well, you might notice after the transform, the ladder stopped being flat. In order to fully understand what's going on, we have to go back to the ladder's own reference frame and then incorporate its location throughout time rather than just one snapshot. After switching again, you'll notice that at any given point in time, the ladder's length is indeed contracted to 3.2 units. But due to the slant, there's a really weird side effect of multiple ladders, which means you're technically seeing an amalgamation of the ladder at different times. In other words, if you see an object traveling at relativistic speed, the back of it is actually in the future compared to the front of it. What I mean by this is if a ship sets up lights to blink in sync, then in the reference frame where it's actually moving, the back lights blink before the front ones. This also explains the ladder paradox, where an 11-foot ladder fits in a 10-foot shed due to length contraction as it moves. In the shed's reference frame, the ladder fits at some point, which we know because you can close both doors at the same time. But this is only by virtue of the multiple ladders phenomenon. In the ladder's own reference frame, it never fits in the shed per se, but it does still fit in one of those weird warped instances of the shed. Since this is what the events of the doors closing were tied to, they're no longer simultaneous. And in the example from the video, since the finite state machine is also tied to the shed, the left signal still arrives first, even when it's not sent out first. Relativistic addition of velocities is pretty similar. If everyone starts at 0, 0, then difference in velocity is just distance between them at time 1. Unlike the slices of the Galilean transform, the Lorentz transform doesn't guarantee this remains unchanged, and that's because velocities don't add. Even though world lines can change slope, they always remain time-like, meaning velocity never exceeds c. If observer A sees observer B going 0.4 c, and they see observer C going 0.4 c, and so on and so forth, then the velocities basically bunch up around c but never reach it. Even though velocity from the original reference frame starts to barely change, you always have plenty of room for it to increase, which is reminiscent of hyperbolic geometry. There's always more space than it seems like. A common way to capture this behavior is to replace the velocity slider with something called rapidity. It's allowed to increase infinitely, and does so linearly in this example. Meanwhile, velocity is a function of rapidity, specifically this one, which is called hyperbolic tangent and approaches an asymptote. You can also go the other way. Even though velocities don't add, if you convert them to rapidity, they do add, and converting back is equivalent to using the velocity combination formula. Also, here's the tachyon example from episode 6. Since it moves faster than c, its world line is actually space-like, a physical impossibility. And because of this, its endpoints swap positions, and Mary is able to send a signal backwards through time. And now it's finally time for the twin paradox. The graph for the acceleration version looks like this. Just by looking at the graph, you could tell Botan doesn't experience time dilation, but Mary does, making her younger. The paradoxical aspect arose from the assumption that the situation was symmetrical. In that case, Mary's perspective would have Botan experience time dilation and therefore be younger. But this assumption is only true if you use the slice technique corresponding to the Galilean transform. In relativity, we have to use the Lorentz transform. Unfortunately, we can't use a single transform to derive Mary's reference frame since it's not inertial. So in order to get the full resolution with all its intricacies, make sure to watch the previous episode. But the Lorentz transform does still provide additional insight in the form of simultaneity lines. Remember, they always have a slope inversely proportional to the world line, so Mary's simultaneity lines look like this. They help explain why she sees Botan age quickly during the turnaround. It's because her simultaneity lines are suddenly shifting. In the limiting case, as the turnaround gets shorter, her simultaneity lines shift instantly, meaning she basically goes straight from a reference frame where Botan's 23.2 to one in which she's already 26.8. As for the inertial version of the paradox, everything still works out, and we get the exact same graphs that we calculated manually in the last episode. And the simultaneity lines again help explain why Mary and RCM4 see Botan at different ages when they themselves are in the same point in spacetime. And the transfer of consciousness just goes from one set of simultaneity lines to the other. The ability to graph pretty much any scenario you can think of makes the Lorentz transform a truly robust tool. If you want to explore it further, feel free to use the Desmos implementation I made, link in the description and pinned comment. But those are all the examples I have today. With that, we've seen how the Lorentz transform recontextualizes every effect and paradox I've covered in the series. But that raises an interesting question about the ordering of things. I use time dilation in my Lorentz transform derivation, but technically the postulates are all you need. For example, instead of using the value of g, we could solve for a using the determinant. So if you instead start with the Lorentz transform, it kind of comes with all the effects for free since they naturally fall out of the math. So why not do things in this order? Well, in my opinion, although it can make derivations more straightforward, it doesn't provide the intuition you get from deriving the effects from scenarios. The goal of this series is to explain what worked for myself, and speaking from personal experience, I could never really grasp the math until I had that intuition for what it even means in the first place. Of course, not everyone has to do it this way. Finding an order that works for everyone is kind of impossible, so it's always good to have options. This is just why I prefer to find the effects without the Lorentz transform at first. However, there's actually one last major relativistic effect I haven't covered yet. I saved it for last because it's not as interconnected with the others and isn't necessary to understand relativity kinematically. But despite that, it's arguably the most famous relativistic effect and has kind of become the face of relativity. In the next episode, we'll examine where it comes from, how it works, and how it naturally leads into both quantum mechanics and general relativity. So I hope you'll join me in the series finale, E equals mc squared. For now though, if you learned something new about relativity today, make sure to like and subscribe. Thank you for watching, and I'll see you next time. Bye!